All right. So yes, I've got the honor of introducing Sergey for his keynote talk today. Sergey, of course, he's been faculty at the Department of UC Berkeley, in the Department of Electrical Engineering and Computer Science since the fall of 2016. His work is focused on machine learning and decision control with an emphasis on deep learning and reinforcement learning algorithms. He really is one of the leaders of getting machine learning and planning systems to work in the real world. He's created a couple of courses on deep reinforcement learning and deep learning, which I'm sure many of us have learned some things from as well, including myself. Many best paper awards across machine learning conferences, across robotics conferences as well. And I personally have learned from him the importance of being able to take the lead. So if there's something you ever think you really could use in your research or in the community, you should probably just go ahead and make it. And that's why I'm very happy to see all of you here today. So with that in mind, I'm very excited to introduce here what Sergey is going to be leading these days. So without further ado, let's welcome Sergey and see you. Thank you.
Thank you, Glenn, for the kind introduction. All right, I figured that for a talk like this, I should start with a little bit of an introduction of my own. That's maybe a little bit more about how I got to this place. So when I was a PhD student in the early 2010s, one of the things that I got really excited about was some of the work that was coming out in this new field called deep learning. And I wasn't the only one. Like that was kind of like the cool thing to start working on that back then. And there were folks like Kwok Lei who had some pretty stunning results where they could take lots of data from the web, train an unsupervised model on it, and have it like automatically pick up like on face neurons and cat neurons. And that was pretty awesome. And there were results like the one from Alex Krzyzewski and his colleagues that showed that you could train a big convolutional neural net on this big data set and actually have it do really, really well at image recognition. This was really exciting because it heralded kind of an era of machine learning systems that were far more automated than anything that came before. Something where it didn't look so much like statistics, but it actually looked like a simulated brain. But of course, an actual simulated brain needs to be, it needs to have agency. It needs to do more than just recognize things in pictures or figure out how to detect cats or people. It needs to be able to make decisions. And when I was thinking about, well, what I thought could be the next frontier in this area, I thought, well, maybe taking these newfangled deep learning systems and actually allowing them to have agency, allowing them to make decisions, allowing them to do control. And since I was working on computer animation at the time, I thought, well, why don't I apply to the kind of decision-making problems that I see in computer animation, which had to do with simulated characters moving their bodies through space, walking, doing that sort of thing. And I thought I should publish this in a machine learning conference rather than a computer graphics conference. So instead of making nice 3D renderings, I thought, well, I'll make the figures look like all the other machine learning figures and have it be like kind of cartoony looking. So that's what I came up with. And I got some nice results with some platforms that some of you might recognize. That's a Hopper and Walker and so on. I copied them from Uvaltasa. I didn't make them myself, but this was the first Mujoko RL thing, shamelessly copied from somebody else. But that same year, Vlad and his colleagues came out with a pretty stunning result that showed that actually like you could scale RL algorithms way up when you combine them with deep nets and get things that do like end-to-end learning of control from pixels. And this was really exciting. And and I really decided that I want to do my PhD in that area. But looking back on this, I see kind of a microcosm of some of the challenges that are coming up today in RL, even early on back in the early 2010s, where if we take a critical look at the things on the left and right side of the slide, although they're both using large deep networks, they're very different in their nature. The successes of the methods on the left side have a lot to do with leveraging very large data sets, typically mined from the web. The successes of all the stuff on the right have a lot to do with being able to optimize reward functions really well in environments where it could generate lots and lots of simulation. And I think this is a kind of a preview of some of the challenges that we're seeing even today with a kind of a dichotomy between the data-driven AI approach and the reinforcement learning approach. So let's talk about that a little bit. These days, if folks in this room are doing a PhD, the things to get excited about are probably large models, things like diffusion models, language models, that sort of thing, foundation models. And these models are based on the principle of taking very large neural networks and training them on very large amounts of data from the web. At some very basic level, these models are density estimators, either unconditional densities or conditional densities. So more or less what we learned about in statistics, fitting some distribution, except now at a very large scale with a very, very complex model. And when we're fitting a distribution, we want to know what will a model learn when it fits that distribution? Well, the first question to ask is, how was that distribution produced? Where did the data come from? There's some process that led to that. And the process for producing data on the web is, well, if it's pictures, it's the pictures that people take and put on the internet. If it's text, it's the buttons that people press on keyboards. So those are the generative processes. So when a model is trained to reproduce that distribution, that's the generative process it's learning about. And on the one hand, it's really exciting to see that such models can produce pictures that look like the pictures that humans might draw and write text that looks like text that people might write. But at the same time, the observation that this is doing density estimation is also a reflection of the limitations we would expect it to have. We would expect it to, in some ways, mimic the typical human behavior that produced that data. And maybe that's part of why it's so difficult, for example, to coerce language models to do what we want, why we have to fine-tune them on very carefully curated data sets or go through a lot of mental gymnastics to design prompts, because they are not actually attempting to achieve some outcome, they're attempting to match the distribution seen in the data. Now, reinforcement learning does something different. Reinforcement learning is all about achieving outcomes. And of course, since the early 2010s, there have been some really impressive achievements in RL as well. I would posit that those achievements are impressive for a very different reason than the modern generative AI systems. So move 37 in the AlphaGo championship match was impressive because it was the kind of move that human experts didn't think ought to be done. It was something that people hadn't imagined in the thousands of years that that game had been played. The pictures generated by generative models today are impressive for exactly the opposite reason, because they look like things that people might do. So they're impressive because they look like something a person might draw. The RL results are impressive because no person had thought of it, because it is an emergent behavior that comes about through optimization. And I think if we actually want those AI agents, like the ones that I talked about at the very beginning, we actually need both those capabilities. We need the ability to synthesize lots of information, figure out how to make sense of the world, but then also find novel solutions to the kind of problems that the agent might encounter. So data-driven AI systems are really great about that learning about the real world from data. And that is an essential ingredient of artificial intelligence. But they make no attempt to really do better than the data. If you actually want them to do something smarter, you basically have to give them smarter data. Reinforcement learning algorithms are all about optimizing a goal and potentially leading to emergent behavior, new solutions that the designer of the algorithm might not have thought of. But they are not making use of real world data in the same way that these large internet scale systems are making use of real world data. So data-driven stuff, all about using data. Reinforcement learning, all about optimization. Data without optimization won't allow us to solve new problems in new ways, whereas optimization without data is very hard to apply to the real world outside of simulated environments like those Atari games or the simulated locomotion tests that I showed. So if we really want to get to those AI agents, we really need to get both of these things in there. So I'm going to postulate that maybe there is a recipe that can make this happen. And I'll tell you about some recent research from my students and myself that maybe provide some of the puzzle pieces that in the future we could imagine being part of this recipe. So the recipe, I think, should start with data, because starting with data appears to work really, really well. And when we start with that data, what we need to do is not necessarily represent the distribution of the data, but extract good behaviors from that data. Look at what's possible in the world and figure out, given what's possible, what should you actually do? What's your best guess about what you should do to achieve your outcome? And that's basically a data-driven offline reinforcement learning process. And once you've done that, you need to not only recover a good strategy for actually solving the problem you want to solve, but actually get yourself prepared to then improve through interaction with the world. So the role of the thing that you should be extracting from that data is a really good initialization, but also the ability to actually improve over that initialization once you actually get a chance to interact. Because one of the big strengths of reinforcement learning methods is their ability to improve continuously through interaction with the real problem that they're trying to solve. And of course, some of you might be wondering, well, why does the pre-training need to actually be an RL pre-training process? Why can't we do like the same kind of generative pre-training and then run a bunch of RL on top of that? And the reason comes back to that density estimation point I made before, that if you are learning about the process that generated the data, well, you're learning about the process that generated the data. If that process was not particularly goal-directed itself, if it was just all sorts of people doing all sorts of different things, or just pictures that people posted on the web, you're not squeezing as much juice out of that data as you can. If you instead treat it as a way to determine the possibilities that exist in the world, the things you could accomplish, and then run an RL procedure to figure out what you should accomplish given that knowledge, then you'll have a much better initialization. There's also a really technical reason for this, which I'll get into later, which is that it turns out to actually be very hard to initialize an RL algorithm with something that is not an RL algorithm. And that has to do with some of the technical details of value functions I hope to talk about a little bit later. All right, so what this talk is really about is what can we accomplish if we combine data and optimization? And I unfortunately won't be able to show you that complete recipe working wonderfully well time after time in lots of different domains. I'll show you puzzle pieces that hopefully in the future could be combined into something like this. I'll start with an overview of data-driven RL algorithms, offline methods, offline to online methods, and some of the open challenges in those areas. And then I'll talk about how some of those ideas can be applied to robotics, generative models, and language models. But let's start with the methods. So what do we need to figure out in order to instantiate that kind of recipe? That recipe that starts with data, figures out how to prepare both a good policy and a good strategy for improving online, and then perform rapid online improvement. Well, we need to do something a little different than classic RL, because classic RL is really all about a kind of blank slate, online, lifelong process. We're doing something perhaps a little distinct. Classically, in RL, we think about an agent that starts from scratch, and learning is driven largely through trial and error. Central problems that we often encounter when we do this: exploration, that's a really big one, sample efficiency, optimization performance. Those are the things that we typically care about in kind of standard reinforcement learning problem settings. In the data-driven setting, we care much more about offline pre-training and online fine-tuning. We would always start from data, and we would expect that that data would actually tell us a lot of what we need to know. The learning process becomes much more representation learning driven. There's still room for some trial and error, but the key is to pull out the right representations from that data that would maximally accelerate that process. And the central problems now are much more about dealing with distributional shift between your prior data and what your policy actually does, providing for scalability and stability, because those are tremendously important, because you need huge models to make sense of that prior data. And being able to apply this to state-of-the-art architectures like transformers, for example. So that's not to say that these challenges are fully destroyed, but there are new challenges we encounter, and old challenges like exploration may become a little bit less central. So to break this down, I can separate it into three parts, and I'll cover those three parts. Offline RL algorithms, online fine-tuning from offline initialization. So offline RL algorithms are basically algorithms that just train on the data. Online fine-tuning takes whatever you got from the data and then trains through some more interaction, and making all of this work with big scalable models. And I ordered these in a very intentional way, because offline RL algorithms are probably the thing that at this point we understand the most among these three. Online fine-tuning with offline initialization we understand a little bit, and making all this work with big scalable models, I would claim, is something we actually hardly understand at all, and it's quite mysterious for reasons that I'll try to explain. So let's start with the one that we understand the best, or at least the one that I understand the best, which is offline RL algorithms. What do we expect offline RL algorithms to do? The setup: you have data, you're not going to be interacting with the world just yet. You're going to take that data and try to distill out the best strategy you can, and ideally also the best initialization for online learning. So let's say you're starting at that green circle, you want to reach the orange circle, and your data looks like this. That's a pretty classical imitation learning setting. You can think of imitation learning as a perfectly valid offline training procedure. And if you do good imitation learning, then this red trajectory might be one of the trajectories your policy will produce. That's great. But remember that we're not just training on good data. We're taking all of this heterogeneous data that we might have mined from the web, and it might look more like this. And now this is where the key idea comes in, that we don't treat this data as supervision in the traditional machine learning sense. Treat it as something that allows us to understand the possibilities, the things we could do. We don't have to do all of these things. So running an offline RL means essentially figuring out, based on what is possible according to the data, what should you actually do to accomplish your goal, which might consist of kind of recombining the bits that you've seen to do something desirable. And the simplest way to explain this is to say, well, if you've seen that you could go from A to B, and you've seen that you can go from B to C, then you should be able to infer that you can go from A to C. But in reality, you can do this everywhere all at once. So if you have lots of suboptimal paths, maybe lots of drivers driving cars in all sorts of ways, every driver is good at something, but maybe not so good at something else. If you can use this to distill out a driving policy that is as good as the best human driver in each situation, it'll probably overall be a lot better than any single human. So if you can benefit from this compositionality everywhere, then you can get something pretty good out of it. So that's kind of the abstract idea. If we want to get into the details of some of the algorithms, we can introduce some notation and then talk about some of the technical challenges. Now, hopefully for the folks in this room, the notation will be very much review. We've got agents, we've got environments, we've got actions, and those are what we're going to be picking. The environment responds with states and rewards. Our goal is to get a policy, I of A given S, and a good policy should maximize the cumulative reward or the discounted sum of rewards or something of that nature. And a very useful object for this, of course, is the Q function. The Q function tells us what is the total reward that we'll get if we start in a state, take an action, and follow our policy. And from this, if we turn the crank or go through the textbook, then we'll arrive at either policy iteration, which means just find a policy that's greedy with respect to your Q function and repeat, or the more popular method, which is Q learning or fitted Q learning, where you write down the Bellman equation, essentially short circuit that process, plug the argmax back into the right-hand side of the Bellman equation, subtract the right-hand side from the left-hand side to enforce this equality at all the states, and you get basically the equation for Q learning or fitted Q iteration or a whole family of other value-based methods. And this serves as a really good foundation for offline RL techniques because Q learning methods do not assume that your state action tuples came from your latest policy. So it is a classic example of an off-policy algorithm, and that makes it a really great starting point for developing offline RL methods. Now, in the early days, we would have thought that that's enough, like we can just stop there, formulate this into some kind of practical algorithmic framework, either Q learning or fitted Q iteration, turn the crank, get out a Q function, recover the policy, done. It turns out that for large-scale problems, even though this is an off-policy algorithm, it is remarkably terrible as an offline method. And this is surprisingly something that people didn't realize until long after the original Q-learning algorithm was invented. So here's the issue. This is the basic Q-learning update. And in deep RL, or in any RL with function approximation, we'll be representing the Q function with a function approximator. And function approximators can be right or wrong. They're trained on data. And whenever you have a function that's trained on data, if you want to know whether it'll be right or wrong, you should ask, well, what distributions are trained under and what distributions are being tested under? So to interpret it for this equation, we'll write it in a slightly funny way. Instead of writing it as a max over actions, we'll write it as an expected value under some distribution pi nu, which just assigns a probability of 1 to the argmax. That's just so I could write it as an expectation. I didn't actually change anything, just made it clear that what you care about is the expected value of Q under a distribution called pi nu. And what was it trained under? Well, it was trained under the data distribution, which I'll call pi beta, beta for behavior. So you'd expect that the Q function matches the targets in expectation under pi beta. And the trouble is that pi beta is not the same as pi nu. So you'd expect very good accuracy when pi beta and pi nu are equal because you're testing under the same distribution they trained under, but they're not the same. And even worse, pi nu was selected specifically to maximize that Q function. So not only are you getting distributional shift, meaning you're testing under a different distribution than you trained under, that distributional shift is intentionally selected to maximally fool your Q function into producing big Q values, which is basically the recipe for getting adversarial examples if the Q function is represented with a deep network. And that is very, very bad. So from this, we might expect that if we naively run Q learning on offline data, we should expect to see Q values that go up and up and up as that maximization exploits your Q function by producing adversarial actions. And in fact, we see exactly this. So the different colors here represent runs of, in this case, it's actually a Q function actor critic algorithm, but the same thing happens for Q learning. Different colors are different data set sizes. The y-axis is reward, and the reward typically goes down because it's not working. And if we look at the Q values themselves, which is how good the algorithm expects the reward to be, the y-axis here is a log scale, so it's expecting something between 10 to the 7th power and 10 to the 20th power, which is a lot larger than negative 250. And that's because it is producing those adversarial actions, fooling the Q function, producing huge values, and then training on those huge values to get even huger values. And that's bad. So this might seem like a very idiosyncratic issue with the Q learning algorithm itself, but the truth is that any offline RL algorithm encounters some variant of this issue somewhere, whether it's a model-based method or a policy gradient method or a Q learning method. Deep down, the issue is that we are asking the algorithm to predict the outcome of a counterfactual action. And if we are selecting that counterfactual action in a way so as to maximize the algorithm's prediction, then we will find the action for which the algorithm makes a mistake in the positive direction, regardless of how it makes that prediction, whether it's a model, whether it's a Q function, whether it's something else. So what are some principles for modern offline RL methods and getting them to work well? Well, there are many different methods, but similar principles seem to be effective, at least today. Those principles might change tomorrow, but so far, it seems like value-based methods work pretty well because it's pretty easy to make them compatible with off-policy data. So Q-learning or Q-function active critic. But we have to somehow fix this distributional shift problem. And it turns out there are many ways to do this. The community, as far as I know, hasn't settled on what is the best way of doing it. I might tell you that my way is the best way, but truth is, I don't know. If I were to bin them into categories, there isn't a standard categorization, but I could say, well, maybe they're pessimism-based methods. There's a lot of great research on all sorts of pessimism-based methods. I'm going to tell you about conservative Q-learning because my student overall came up with it, but there are many others that are great too. The basic principle behind all these methods is if you are not sure what the value should be pessimistic. There are constraint-based methods, which basically say, well, don't try to mess with the values, but instead just avoid actions that are too far from your training distribution. Perfectly reasonable thing to do. And then there are some other more exotic methods that, for example, even try to rewrite the Bellman equations in a way that you don't never actually have to evaluate actions that you didn't train on and use some kind of exotic loss function so that you can still get a maximization effect, but never have to plug in counterfactual actions at all and rely on the generalization power of the network. So there's all sorts of clever ways of doing that. I'll cover the pessimistic approach because it's pretty simple and I think there's some nice intuition behind it, but that's not to imply that it's the best method, just that it's kind of a nice didactic example. So conservative Q-learning is an example of a pessimistic approach. The idea is that it's trying to deal with this overestimation problem. And here's the intuition behind how it does it. Let's say you have some function that, in this case, it's going to be your target values that you're trying to fit, shown in green, and you fit that function kind of okay, shown in blue. So blue is your fit. Now, the blue fit is pretty good in most places, but of course, if you take the argmax for that blue curve, you're going to pick exactly the point where you get the biggest error in the positive direction. So the principle behind pessimism is, well, let's find those points and let's push them down. So let's actually push them down like that. And the way that conservative Q-learning implements this is by formulating an objective with two terms. The bottom term is just the regular fit Q duration objective, so that's just Q-learning. And the top term on the first line is a regularizer. And what that regularizer does is it finds actions that have a high Q value and minimizes them. Now, if you were to just do that, then you're creating kind of downward pressure on the whole Q function. So you would expect to systematically underestimate the Q values. So what you do to compensate for that is you take the actions in the data set and you push them up instead. And that's what the second term, the minus term on the first line is doing. Now, it might seem kind of weird because we're dealing with overestimation, but we're pushing something up. But imagine that your policy perfectly matches the data, which means that the actions in the first expectation are exactly the same as the actions in the second expectation. Then you'd expect these two terms to perfectly cancel, and the regularizer does nothing. So it turns out that you can actually prove, even though you're both pushing up and down, that this would actually never overestimate your values. It will actually systematically be less than or equal to the true values. So that's pretty neat, of course, if you choose the regularizer weight to be large enough. And remember how I mentioned that this problem is very deeply linked to adversarial examples. This maximization is an issue because it'll find actions that exploit the Q function. Well, this is very deeply linked to adversarial training. In adversarial training, you also try to find directions where you'd improve and push them down. So it makes sense. The problem looks like adversarial examples. The solution looks like adversarial training. Now, there are other ways to do offline training, but they all kind of deal with this distributional shift problem in some way. And typically the way they deal with it is basically ends up correcting that overestimation problem. So let's talk about online fine-tuning. And we'll talk about online fine-tuning from conservative Q-learning. But again, the same principles might apply with other algorithms. It turns out that if you just train with conservative Q-learning on offline data and then run online RL, we're going to have a pretty big problem. And we tried this. We thought it would work fine. We tried it really hard, and we had a problem. So what this curve is showing is roughly the performance of the agent. The x-axis is the number of training steps. And here at 50,000 steps, we switched from offline training to online training. During offline training, the agent got better and better and better. Of course, the agent didn't know it was getting better because it was offline, but we evaluated it in the background without telling it, and we know that it was getting better. And as soon as we deployed it for online training, performance drops. And then it gradually climbs back up again. But of course, that's a lot of waste of time. And if this agent was, for example, driving a car, it's not just waste of time, it's also wasted cars. So that's not good. And if we actually look at the average Q values, the average value of the Q function on states in the data set, turns out that over the course of that offline training, the average value is dropping and dropping and dropping. And once the agent is deployed in the real world, Now I realize its values are better than I thought they were, and they climb back up. So the reason for it is that even though we have that second term in the conservative Q-learning algorithm, it still actually underestimates. It's still systematically producing values that are lower than the true values. And that makes sense because it's going to be choosing counterfactual actions. It's going to be choosing actions that are different than the ones in the data set. Otherwise, how could it possibly improve? And insofar as it chooses actions that are different than the ones in the data set, it's going to underestimate their values systematically, which means that when it gets to go and interact with the real world, now it's suddenly realizing that those actions for which it was estimating lower values are actually pretty good. And it experiences big error and starts pumping those values back up. And as it's doing that, it throws the entire function approximator out of whack, resulting in that red chunk of wasted time. So it turns out that there's actually a remarkably simple solution to this, which is very easy to implement, but somewhat tricky to understand. So the key idea is to put those offline trained value functions on the right scale. Basically, the value functions they're basically representing the right idea that relative values of different actions are more or less correct, but they're all systematically pushed down like that. And just for shorthand, I'm going to refer to this notion as calibration, meaning the overall bias on the Q function. So we're going to say that a calibrated Q function is one where the learned values upper bound the values of some real policy, meaning that there's at least some policy for which you're not underestimating. And conservatives means that the learned values lower bound the value of the learned policy. So of course, if you're calibrated with respect to learned policy and you're conservative with respect to learned policy, that means you're upper bounding and lower bounding, which means you're exactly correct. That's too much to expect. You will not get that. But at least you could say, well, let's be calibrated with respect to some real policy, some policy that actually exists, and conservative with respect to your learned policy. So then there's going to be a gap, but at least you can limit that gap by choosing a good policy to calibrate against. And surprisingly, it's enough in theory to be calibrated with respect to any reasonable policy. And I'll tell you what reasonable means in a second, to get efficient online fine-tuning. Efficient meaning that you can put a bound on the sample complexity and that bound doesn't look horrible. The bound is actually better as the policy you're calibrated against gets better. And the best bound, of course, is obtained when you're calibrated against the policy you're learning, because then you have exactly the right Q values. So how do we practically ensure that our Q function is calibrated? How do we practically ensure that it upper bounds the values of some real policy? Well, before we were minimizing the Q values. Now, what if we minimize them, but we clamp them so that we never minimize them past the value of some policy mu? Okay, we'll just put a floor on our regulars, say never push below the value of some real policy mu. And then we just need to get a value for some policy that actually exists. But it needs to be a correct value, at least an expectation. Well, it turns out that there's one policy for which it's pretty easy for us to get the value, which is the behavior policy, because the behavior policy is where our data came from. So we can just average to get together the rewards, sum together the rewards in the data set, regress onto that, and that gets us at least an unbiased estimate of the value of the behavior policy. It's still going to have sampling error, but at least it won't have systematic bias. So that's a pretty good choice because that's the one policy that we can evaluate pretty easily. Let's plug that in there. And then the spoiler here is that the bound you're going to get is going to be better as your behavior policy is better. That makes sense. Like if you have really good data, then you'll have a pretty good bound. If you have bad data, you still have a bound, it's just not as good. Makes sense. So that's the method. We call it calibrated Q-learning, not the most original name. And it's basically conservative Q-learning where the only change is to put a floor on that minimizer. So the only change is that first term on that first line where we don't minimize the Q function below V pi beta. That's it. So the minimization ensures conservatism, putting that floor ensures calibration against the behavior policy. And as a result, we actually get an offline pre-training online fine-tuning method that actually works. So I won't go through the actual statement of the theorem. The theorem intuitively states that online RL fine-tuning is provably efficient, meaning low regret with a polynomial bound, if the pre-trained Q function is both conservative and calibrated. And how efficient it is depends on how good the policy that is calibrated against is. Empirical performance, benchmarks, lots of plots. The important bit, the red line is CalQL. The red line is this method. The green line is CQL. That's the method I presented before. The red line is pretty good. The red line usually doesn't have a dip. So sometimes you still get that dip. Sometimes you still underestimate and climb back up. CalQL makes it a lot better, but the problem is not fully solved. And I will tell you, in all honesty, the problem gets worse as the tasks get harder. And that's the bad news. So the benchmarks, there are RL benchmarks. RL benchmarks are not that hard. Real world problems are a lot harder. So definitely a step in the right direction, definitely a big open problem as far as how to fix the problem for real. So if you are interested in problems like this, there's plenty left to do. Okay, so that's online fine-tuning. Now, the third part that I promised to talk about is what it takes to make this stuff work with big models. And that's the most mysterious thing, the thing where I'm going to have probably the least intelligent thing to say, but I hope to at least give you sort of a hint as to what the problem is, at least insofar as I understand it. So first, let's start with something like very practical and empirical, some good news, right? And deep learning, this is like the history of deep learning. The empirical performance is usually good news. The conceptual, theoretical stuff is usually bad news. So we'll start with the good news. We were pretty excited about CQL and CalQL, and we thought, well, why don't we take a whole bunch of different Atari games, train one really big network on all of those Atari games from suboptimal data with offline RL, and then use it for, well, playing the Atari games and also fine-tuning to new games. So if we just train on 40 different Atari games with suboptimal data, we get pretty good performance. I won't go into detail about the bar graphs, but it works. And then you can, it improves over kind of non-Q learning based methods. But then you can take that offline trained Q function, you can fine tune it to new variants of the games or new games entirely. You can fine tune it with offline data. You can basically do offline fine tuning. You can also fine tune it with online interaction. The pink bar, the one on the far left here is the CQL based method with the multitask pre-training. And it works. Like you can actually get this multitask initialization, fine tune, big models, they accelerate online training, kind of very much like that recipe at the beginning. But it's hard to make it work. It takes a lot of tuning. It takes a lot of hyperparameters. It's not a turnkey solution. It doesn't seem to ever work quite on the first try. So we thought about this and we figured, well, maybe we need a better explanation. Like, why is it so darn difficult to make these things work well? We don't know exactly why that is, but we have a few ideas. So it's especially annoyingly hard to make this work with larger and more modern architectures. Transformers seem especially bad, and that's bad news because you have to have transformers. It seems to require larger models with more capacity than we might expect. So we can get a gauge for how big of a model we think we need by running, let's say, imitation learning on a really good data set. And it turns out that we need a much bigger model if we want to do RL. That's kind of weird. I mean, there might be some explanation, but it's still kind of weird. So something about RL, specifically TD learning, Q learning, or Q function actor critic, seems harder than supervised learning, harder in quotes at least. And we did some experiments, or rather, Aviral Kumar did some experiments, and Aviral found some pretty interesting stuff. So let me tell you about this plot. There's a blue line and a red line, and it's a little subtle what the blue line and the red line mean. So both curves are doing policy evaluation. There's a reason why we did policy evaluation instead of policy improvement. They're just doing policy evaluation. The red curve is SARSA. So the Q function is updated to be R plus gamma times Q of S prime A prime, SARSA. Offline SARSA, so the data is not changing. The blue curve is almost like SARSA, except for the next action, you resample it from the behavior policy. Now you're resampling from the same policy, so an expectation that action comes from the same distribution, which means that the blue curve should look just like the red curve in expectation. It has the same targets. But the blue curve looks very different. The blue curve looks very unstable. That's very strange. That's very strange because the targets they're coming from the same distribution, just one of them resamples the action and the other one doesn't. Here, of course, your actions, they're arranged into a trajectory. So the action A prime from the data set is the action A at the next time step, but the resampled action isn't. So that's the difference. But we wanted to get a better sense for what this instability really is. And we made another plot, which is a little bit more subtle. And this plot is showing the dot product between the features inside the Q function network for SA and S prime A prime. That's a little bit of a weird choice. So what I mean by features is you have a network that takes in S and A, and it has some last layer features, and those last layer features have a linear layer that reads out the Q value. So what this plot is showing is the dot product between the last layer features for time step T and time step T plus 1. If those dot products get big, that means that current features are very similar to next features. If the dot product goes to 0, that means that you have orthogonal features for the current time step and the next time step. So roughly speaking, you can think of this as kind of indicative of aliasing between the current step and the next step. If you're really good at discriminating current step and next step, you'd expect to see smaller dot products. If you're really bad at discriminating, you expect to see large dot products. And you see large dot products for the blue thing and low dot products for the red thing. Now remember, the red thing is SAR, so the blue thing is resampling the action. The reason that we did it this way instead of doing improvement, of course, is that you can't do offline RL with SARSA and improve the policy. So you can't put in the max with SARSA. You can put it in for the blue thing. So roughly speaking, that blue thing is kind of meant to represent what you would get if you were to run real Q-learning. Of course, if we run real Q-learning, you can't compare it to SARSA. So what does this mean? This means that when we're resampling the action from some distribution, even if it's the behavior policy, probably even worse if it's not, you're getting this instability, and the instability manifests in bad representations. Bad in the sense that the dot product of current features and next features is big, which means current features are starting to alias against next features. Bad representations. All right, so we have a hypothesis about why it happens. I think this hypothesis is reasonable, but I can't promise you it's completely correct. The finding is that TD learning hurts internal representations. So then we could ask, why do deep nets learn good representations in the first place? Like supervised learning seems to learn good representations. What's the mechanism? And there are a few ideas that people have. One idea is implicit regularization. So a deep network is overparameterized, which means that if you train enough, you're going to get very, very low training error. Conventional models of regularization don't necessarily apply. But you could say, well, maybe because you're running stochastic gradient descent, or maybe because neural nets are really good in some way, you will get a zero error solution that will be regularized. So among all possible zero error solutions, you'll get a good one typically means something like a solution with a low parameter norm. And there are many works that analyze this and show that under various models of SGD or various models of implicit regularization, you get something reasonable. So you can take one of these models and you can apply that to TD updates instead of regular gradient descent updates. So we took the model from these two papers, and the model basically suggests that what you actually minimize in supervised learning is the norm of the gradient. For a linear model, the gradient is the feature vector, so you're minimizing the feature vector more or less. That makes sense. If you do that for TD, you get two terms. The top term looks a lot like the original supervised learning term, so it's basically saying that under some matrix, you're minimizing the squared norm of your gradients. That's good. You want to minimize the squared norm for gradients because, roughly speaking, if it's a linear model, the gradient is the feature, so that means you're minimizing the norm of your features. But the second term says there's a negative sign in front of it. You're maximizing the dot product between the next gradient and the current gradient. And if these are linear models, that's more or less the same as maximizing the dot product of the next features and the current features. Exactly what we actually see in practice. So what does that mean? That means that the magic that makes supervised deep learning work well, this implicit regularization effect, might actually make TD work poorly in the sense that you get this feature aliasing effect. Okay, so there's a lot that went into turning the crank on this and getting out this hypothesis. A lot of us, as with all kind of theoretical work, a lot of assumptions. Can't say for sure those assumptions are necessarily correct, but the implication is there. The implication is that something about TD updates is not as wonderful for representational learning as supervised learning is. And in fact, other works have corroborated this high-level idea, although they postulated different mechanisms for it. Work on dormant neurons, work on learning dynamics and plasticity. They all postulate different mechanisms, but for a somewhat similar phenomenon, which is that whatever it is that happens in the TD learning process just doesn't produce representations that are quite as nice as the ones that we get out of supervised learning. So I think if I were to be honest about this, I would say we probably don't actually know the mechanism. There are a number of different ideas. Maybe the truth is somewhere in the middle, but the issue exists. So no current model fully explains what's going on, but it's clear that representation learning with TD is not as clear cut as it is with supervised learning. And that's more or less all I have to say about it. So if you are doing research in this area, this might be something to check out, because I think this is a place where the really juicy open problems might be. So summary and takeaways. Offline RL, I think, is an essential component of data-driven RL. We have to handle the distribution shift between offline data distribution and the new policy. Online RL fine-tuning from offline initialization presents new challenges, and we have to be able to fine-tune online RL. And doing this with large models presents yet more challenges, many of which we don't fully understand. So that's the algorithm situation in a nutshell. What I want to tell you about for the rest of the talk is material that has a lot less math and a lot more videos, hopefully, to tell you a little bit about application of some of these ideas, that original recipe with training from data and then doing online fine-tuning. How could it actually work in practice, and can we get a little preview of that? I'll talk about robotics first. I've worked on quite a number of large-scale robotic RL experiments. Many other folks have worked on
all sorts of large-scale RL experiments in robotics. Just to provide a few highlights from my own past work with colleagues at Google, we developed a grasping system for robotic arms that could get 90% plus grasping success from 500,000 autonomous attempts through a hybrid offline-online algorithm. We actually extended this algorithm to be able to collect data in real office buildings. It was actually a combination of these classroom environments and real office buildings, and showed that we could deploy this in the real world. We also showed that we could train language condition policies with imitation learning, roll out the imitation learning policies, get autonomous trials, and then even the failures from those autonomous trials could be included into an offline RL recipe to improve the policy. So these things can actually work at scale. But what I want to tell you about today is some work that my students Drew and Kyle did that tried to actually complete that loop of the offline pre-training followed by online fine-tuning, not in the domain of robotic arms, but specifically for robotic navigation. So this work started with a project called GNM, which aimed to produce a general purpose robotic navigation policy by taking data from many different robotic platforms and training a single goal condition policy on all of these robots. And that goal condition policy could actually generalize pretty well. It could control robots in a variety of different environments, and it could even generalize to new robots. Like it could fly, for example, the drone in the top left corner of that video, even though it was drones. Now, the drone is pretending to be a car, so it's flying at a fixed altitude. But other than that, it is a new platform with a new camera view and so on. So we're getting a fairly general policy from this offline training procedure. But then what we wanted to do is we wanted to see, can we actually do online fine-tuning for this and actually adapt it to a new problem? The problem that we wanted to adapt it to was racing at high speed through Soda Hall in Berkeley, because that seemed like a fun thing to do. And we did offline pre-training on that multi-robot data set, and then online fine-tuning on a new robot, on a little RC car. And the online fine-tuning is basically doing end-to-end RL from pixels to drive the car around this building. In the beginning, 5 minutes in, it's not very good. It bumps into a lot of things. It's a new vehicle. It's actually a new action space because now it gets to control speed. Before it didn't control speed. But after just 15 minutes of training, it's actually able to make quite a lot of progress around the building. Still collides into walls occasionally, but 15 minutes in, this is much further than I would expect an algorithm that learned from scratch. After 25 minutes, it actually drives at about the same speed as the lead author on this paper could drive it if he was constrained to use the same first-person view. Turns out that if you got a third-person view, you'd go a little bit faster. So here's the first-person view, and it really is quite a bit harder. So that's pretty neat, 25 minutes to get to like roughly human level performance from pixels. Of course, the key there is that pre-trained initialization tells the vehicle almost everything it needs to know about obstacle avoidance, and what it has to do during fine-tuning is just learn how to step on the gas and adapt to the particular camera viewpoint and dynamics of this vehicle. The same thing works outdoors. So here it is racing on the grass. There are checkpoints on the grass that it has to go through, but in between those checkpoints, it really likes to go on the concrete path. Well, for a pretty obvious reason, because on the concrete path, it can floor it without worrying about undesired events. Here's the first-person view for the grass racing. So that's pretty neat that we can do offline pre-training, we do online fine-tuning, and the online fine-tuning actually acquires some new behavior that it didn't have just from the offline training phase alone, and the offline phase actually accelerates the online phase pretty significantly. Now, these were kind of one-off experiments in the sense that the online phase is not really trying to improve that generalist policy. The online phase is just trying to make it race that one circuit. So more recently, what we really wanted to figure out is, can we actually have a more lifelong process? Can we pre-train on that offline data set and then continuously improve through autonomous exploration of an environment? So we set up an experiment where we actually used the same kind of CalQL framework to get a little TurtleBot robot to learn to navigate around our office building. And what this robot is doing is it's actually setting goals for itself, trying to achieve those goals, and in the process, improving its generalist policy. It gets pretty good coverage of the building. So the leftmost heat map shows the coverage it got in our office building. It's about as good as it gets without going to the bathrooms. It was geofenced, no going to bathrooms, no going down the stairs. And it actually got the highest success rate compared to GCBC, which is basically an imitation style method, and RLPD, which is a purely online method without the offline pre-training. So something here is actually working. You can do offline training, you can do online fine-tuning, and the online fine-tuning can actually turn into a lifelong process. The same kind of thing can be done for manipulation. Robotic manipulation is a little bit more complicated because there are many tasks you can do, so you need a more sophisticated kind of harness to make all this happen. The harness turns out to be pretty accessible from modern foundation models. So a vision language model can look at the scene and say, what can you do here? Well, I can take the banana out of the silver pot. A diffusion model can generate a picture of that hypothetical image And that can be used in the same kind of lifelong learning scheme with offline pre-training and online fine-tuning of the goal condition policy. It's a more complex pipeline, but similar principle. And what that actually looks like is this: lots of robotic arms inventing various tasks that they could try, moving objects around, and using that to continually improve from their offline initialization. If we run this in a variety of target environments, we get about a 2x improvement in performance on those target environments, which is, of course, not that surprising because you're literally fine-tuning to that environment, so you'd expect to get better. But it's a good confirmation that even in these fairly elaborate multitask settings, you can actually get this autonomous improvement. More recently, I and a number of my longtime colleagues started a company called Physical Intelligence that is aimed at actually producing robotic foundation models at scale. I don't have particularly deep scientific results to show here yet. I hope to be able to show that in a few months, but as a preview, here are a few videos of the kinds of tasks that I hope the next generation of robotic foundation models will be able to do. And these are currently works in progress. All right, for the next section, what I want to do is I want to summarize how we can use similar ideas in very different areas, not in robotics, but for actually bringing RL ideas back to generative models and also extending them to language models. So far, we talked about basically taking the big data set recipe and bringing it to RL. But what about the other way around? Can we bring RL back to these data-driven AI techniques and actually make them better? So as a reminder, the generative methods are impressive because they generate pictures that look like pictures that humans might draw. But we don't necessarily always want that. We want new pictures. So what if we want some novel invention? What if we want Stable Diffusion to make a picture of a dolphin riding a bike? If you take that prompt and you plug it into Stable Diffusion 1.4, this is the picture you get. I realize that 1.4 is an old model. This work was done some time ago. For this particular prompt, if you plug it into a modern diffusion model, you'll probably actually get a picture of a dolphin riding a bicycle. So the work would need to be updated. But pretend we took a time machine to 2 years ago, that's what you would get. Why? Well, because dolphins riding bicycles is not something that people draw very often, and certainly not something that people photograph and put on the internet. Now, why? Why is this happening? Well, it's in some ways, it's a little bit like an artist's Move 37, right? Like, what is Move 37? It's a novel solution to a problem that the agent encountered. This dolphin riding a bicycle requires a novel solution. It doesn't just require regurgitating the kind of pictures that show up on the web. So we need optimization to get this emergent behavior, to get the emergent behavior of drawing a novel picture. And here's how we can do it. We can actually set up an RL problem to generate not necessarily better pictures, but pictures that better align with what we requested. So we're going to have the following system. We're going to have our diffusion model take in a distribution of prompts. We need to construct that distribution. That's what we're going to train on. It's going to produce some pictures, and then we're going to show those pictures to a vision language model, to Lava, and ask it to tell us what's going on, what's in this picture. And then we'll compare the output of Lava, which is basically going to serve as our reward, to the original prompt using some language similarity score, in this case, BERT score, and assign a reward based on how similar they are. This might seem a little circular because the diffusion model is trained on lots of data from the web, and so is the vision language model. So where does the benefit come from? Well, remember that the diffusion model is just trying to model the distribution of images that it was trained on. It's not actually aware of the fact that when you give it some piece of text, it should actually produce pictures that align with that text. It's just trying to predict what are the pictures that tend to occur on the internet, conditioned on the textual description. So it's actually, in a subtle way, a different objective. So it's teaching the model to solve the task, which is to actually make something that reflects that prompt, rather than just copy the data distribution. Subtle, but a very important difference. Now, there's a technical challenge because diffusion models are not easy to train with RL. So reinforcement learning algorithms like policy gradient methods work really well for function approximators where you can evaluate log probabilities in closed form, and so that you can take their gradients. That's the basic operation for policy gradient. Diffusion models really don't make this easy. So instead, what we can do is we can treat the diffusion process itself as a dynamical system, compute gradients through each step of the diffusion process, treating it as though it was a policy, and actually do multi-step RL, even though we're really only generating one picture. So each diffusion step is a step in the MDP, and the reward is just assigned at the end of that process. So we call this algorithm DDPO, and very simple idea, just treat every step of diffusion as an MDP. You get a policy gradient expression, very similar to a regular policy gradient, but now over the steps of diffusion, and it basically works. In fact, it works a lot better than things like filtering or weighting. There's some concurrent work that proposes a fairly similar technique called DPOK, but the concept is essentially based on the same ideas. So we can walk through what it looks like to optimize these prompts. Now, remember, there's a distribution of prompts, and many prompts are being optimized in the background, but I'll just show the dolphin riding a bike. This is what we start with. That goes into Lava. Lava assigns a reward, and a few iterations later, we start getting a picture like this. A few iterations later, it looks like this, and a few iterations later, the dolphin becomes a pretty crisp dolphin. There's a second dolphin that shows up for good measure, and somebody somewhere is riding a bicycle. So I would say that's like a pretty coherent improvement. I don't know why the second dolphin is there. I guess dolphins travel in pods. Remember, we're optimizing a distribution of prompts. So here are more samples from that distribution. It's all animal doing activity because, hey, that's fun. For some reason, they all become cartoony animals. I'm not really sure why. The interesting thing is that some prompts are easier than others, and the easy prompts actually kind of lift up the harder prompts, which is exactly what we might expect from a multitask training procedure. So that's pretty neat. Okay, in the last section, I'm going to discuss how these ideas can also be applied to language models to build language model agents. So why might we want to use our multi-step RL algorithms and offline RL algorithms for language? Well, because we can use it to interact better. So we could, for example, take a corpus of data, let's say like the Ubuntu dialog corpus or something, plug it into a box, of some kind of algorithm, have that algorithm train up an LLM, and somehow that algorithm should analyze those dialogues and figure out how do you interact with humans in a way that is better than the average human. So if you just copy the dialogues in your data set, that might not lead to great performance because, hey, these are just scraped from chat rooms. So some of them might be good, some of them might be bad. You don't even know which ones are good because what you care about is not whether you said something nice, but whether you solved the tech support problem. So just copying isn't going to work. But the data tells us a lot about how humans will respond. If you analyze that data more like a psychologist, understand what kind of statements lead to what kind of answers, then you could synthesize that knowledge and come up with a better agent that is more effective at solving the problem. So that's what we want our algorithm to do. How can we leverage these patterns to do better than humans? So let's turn this into some kind of sequential decision-making process. This is an example. The illustration here is from a visual dialogue task, not exactly tech support, but it's a benchmark task in this area. And we'll say that we have observations, which is what the other person said. We have actions, which is what we said. And these actions and observations alternate. Our state is going to be a history state, so it's a partially observed problem. And our reward is going to be the dialogue outcome. And typically the reward will only be known at the end. This is a guessing game. It's like 20 questions. So the reward is, did you guess the right thing? In tech support, the reward is, did you solve the problem? Crucially, this is not the same as RLHF. So RLHF is about learning from human preferences. In RLHF, a person tells you, do I prefer this answer over this answer? This is learning from outcomes. And outcomes are determined by a dynamical process that is not differentiable and not known to you. So a successful tech support agent solves the tech support problem, even if they say something that a person would rather they not say. And that's a very, very important distinction because that requires using multi-step reinforcement methods. So since I'm running a little low on time, I won't go into great detail about the methodology, but at a high level, what you could do is you can actually formulate a MDP where every single token is actually a time step. And instead of associating a probability with tokens, you're going to tokens. It turns out to not be that hard to set it up because you can, in the same way that you can impose a loss on each token, typically a max likelihood loss. If you want a Q-learning method, you simply impose a TD loss on each token. Take the next token, compute its value, add the reward, and formulate a loss that way. Very much like regular Q-learning. Regular language models predict the probability of the next token given the previous tokens. In this case, the Q values predict the probability of success given the new token you've selected and all the previous tokens. So in the interest of time, what I'll do is I'll skip through some more of the details, but the additional thing that we need to make this work really well is to generate lots and lots of synthetic data. And synthetic data turns out to be really easy to generate with LLMs because, hey, what are they doing? They're predicting what buttons people will press on keyboards. So if we take that Q-learning idea and generate lots of synthetic data with LLMs, then we can get agents that are very effective at solving some pretty interesting interactive problems. Here is a teaching example. This is a baseline. This is ChatGPT. And we prompted ChatGPT pretty carefully to be a very interactive teacher. So the human says, hi, I've been hearing about something called behavior coding in AI, but I don't really know what it is. Can you explain it to me? And it starts explaining, and it does this kind of wall of text stuff that ChatGPT does. The agent trained with RL says, I'd be happy to explain behavior cloning. To start, could you tell me if you've ever come across the term artificial intelligence or machine learning before? And then it asks, let's take it step by step. Have you ever used a computer or smartphone? Now, this is much more like how a person talking to another person might behave. They're actually trying to elicit information about the student so that they can explain the concept better. And that's the difference that you get by actually reasoning about the sequential nature of the problem. All right. I will skip over this part because I do want to come to my conclusion. I talked about what we can accomplish if we combine data and optimization. And I want to end on a little bit of philosophy, a lesson about data and optimization. This is something that became really crisp to me when I read Rich's excellent essay, and I'm going to basically offer my interpretation of it. For those of you that haven't read the essay, I imagine that most of you probably have. If you haven't, do go and read it after this talk. It's excellent and is the most concise and clear-headed statement of the kind of basic dogma of modern machine learning. But the two-sentence summary is this. We have to learn the bitter lesson that building in how we think does not work in the long run. The two methods that seem to scale arbitrarily are learning and search. Now, some people read these sentences and they come away with the conclusion that this means that we need to shovel more data into GPUs. That's not a bad conclusion, by the way. I actually fully approve of that statement, but the essay says a lot more than that. And you'll notice that there are two words, learning and search. And I guess we all know what learning is, but why is the word search there and why is it placed on an equal footing? Well, because it's really important. So here's my interpretation. Learning is about using data to extract patterns. You go out into the world, you grab your data, and you figure out what's going on in the data. What are the patterns? To me, what search means is doing some additional computation to analyze the patterns you've pulled out to actually find something more, something new. Search isn't about going and getting more data. Search isn't about finding new patterns out there in the world. It's about kind of ruminating on what you've acquired and somehow becoming smarter as a result of that. So to me, it means optimization. So my own interpretation of this, and maybe Rich will disagree with me afterwards, or maybe he'll agree, I don't know. But this is my interpretation, is that what we really need is a combination of data and optimization. The data will allow us to understand the world as it really is, and the optimization will leverage that understanding for emergent behaviors. Data without optimization won't allow us to solve new problems in new ways, and optimization without data is hard to apply to the real world outside of simulators. And that's the lesson I took away from that essay. Maybe I got it wrong, maybe I got it right, but I kind of like that lesson. I'd like to thank my students who carried out much of this research. I'd like to thank you all for listening.
Got time for a few questions? Go ahead.
Sergey, thanks for the talk. Yeah, I know. So I was thinking about the correlation that you were talking about when you're doing TD and how it's managed by representations. And there's this other line of work that there are a couple of papers that have been written right now that say that if you want to do RL, you should do the classification and not regression. And somehow I feel that's related because it's you can talk about learning representations with neural networks, but maybe we can even go even simpler, say using neural networks with reinforcement learning. So how much of that do you think it's about the fact that we're doing regression instead of classification to predict those values? Do you think it has to do with the representation that you're learning and the correlation between the two states that are? So do you have any thoughts on that? I'd like to
It's a really good question. I don't know, and I do think that's sort of like the classification loss thingy is mysterious and the representation issue is mysterious. So if two things are mysterious, then they're probably related, right? But yeah, the truth is I don't know. The dot product thing does happen with other losses, so that's not just a squared error regression problem. But the cross entropy loss seems to help, so maybe it has something to do with it. Certainly, it makes training big models easier, but I don't know why.
Thank you for the talk. And I guess my question is for like offline RL, like the TV. You mentioned that kind of learns about representation of like the states. And I guess like in the idea of like retraining the supervised learning, you learn the data distribution pattern, you would know like I guess my opinion is like you learn a good representation of the data and then you say, okay, hey, give me this goal, now I'm gonna go execute it. Why do you choose like offline reinforcement?
Yeah, this is a great question. So, in fact, there is a significant body of work that basically formulates representation learning objectives that look like next step prediction objectives. And there's a lot of theory that analyzes those in terms of linear MDPs to show that actually those representations can be really good for TD. And I think it's actually entirely possible that the representation learning aspect of the problem could actually be tackled with methods that are not TD methods, that are dedicated representation learning methods. At the same time, I think it's very difficult to, in a very complex problem, like for example, that driving robot that I showed, to start off with something that is not a complete value function. Because in the real world, you don't just want to start off with raw representation. You want to start off with skills. You want to start off with something that will at least make it so that when I try to walk down the stairs, I'm not going to fall off the stage. So I think representation learning alone is probably not enough for truly safe and efficient initialization of online RL. I think we can do better. But I do think that there's something very frustrating, which is that actually, in many cases, initializing with representation learning actually works better than initializing with offline RL, perhaps because of that representation issue. And that's a mystery, I think, for us to resolve.
Thank you.
Hi, Sergey. Thanks for the great talk. My name is Shalom from Toronto. So my question is about benchmarks. I guess when we had ImageNet in 2012, it's kind of the North Star that field computers work towards, and now that we have generalist policies, whether it's LLM agents or something else, it seems like there aren't good benchmarks for evaluating, or there's not a good way to evaluate these agents, especially if they're generalists and they're not training on a specific set of tasks. So now, let's say you had infinite resources and infinite manpower. What is the North Star benchmark that you think we should be working towards for a generalist policy?
That's a really good question. I think it's a really difficult question to answer because reinforcement learning is it's a different type of thing than computer vision. Like computer vision is an application. Reinforcement learning is like an entire area. So it's like saying like, what's a benchmark for like supervised learning? That's not to say that we shouldn't try. Like I do think that great benchmarks help orient the field and push people to solve the right problems. But I think it's really difficult. And I think that in some cases, actually pointing the research into the right direction is every bit as hard as actually doing the research. So very good question to ask. Definitely not something I can answer right now in 30 seconds, but it is something that we as a community ought to discuss and think about really, really carefully.
One of the questions, if there's time, regarding, you briefly went over the example of the language model asking questions to the student and kind of modeling the student before it starts teaching it. This to me seems like a very hard task for language models. Modeling kind of it needs to assume as if it doesn't know something, and then think about how the student, what's the best way to present the information so that the student learns about it. I maybe have thoughts on kind of having the model think as if it doesn't know something which it does know.
Yeah, this is I could probably talk about this question for a very long time because I think one of the really deep mysteries about language models today that I think actually people are making a lot of progress on. This has nothing to do with reinforcement learning. The mysteries about how language models represent their own uncertainty and self-reflection. And it's weird, like it is definitely not what we would expect from a cursory understanding of regular shallow models. And I think that what you're asking is a really great question. I think there's probably something that language models do extremely well, but also something that they might have no way of doing. Like, you know, there's all sorts of complicated processing how a person learns a concept. And I think that there's a lot of really fascinating research that could be done to better understand how language models represent their own ignorance or uncertainty and how that evolves over time and whether that can actually be leveraged to achieve some of these things. But yeah, it's a very complex topic.
Thank you.
So thank you very much for the great talk. I really like this DB problem. And so I'm going to ask something about that. Normally when we do DB, we do it on trajectories, right? So this is sort of like now with the buffer where you sample and then, your inputs and your outputs don't quite match, don't quite align. So I'm wondering to what extent do you think this problem is caused by us trying to do this kind of sampling of transitions and sort of the expectation on the target further compounding that. So in some sense, you are false, even if you are in expectation not. Or is it just some completely other?
I think I see what you're saying. I'm trying to think of how to answer it in an intelligent way. Okay, so maybe like a few clarifications, but I think we're probably on the same page here. The experiment I showed, the transitions were arranged in trajectories. So for SARSA, A prime was actually the A of the next time step. When we're resampling the action, we're of course violating that. Like now we resample A prime and it's not actually the A of the next time step. And I think that is actually fundamental because if you were to actually try to improve the policy, you necessarily would have to get a counterfactual. So my interpretation is that this is not like a quirk of SARSA versus this other weird algorithm, but it is actually fundamental to off-policy RL, because in off-policy RL, you want counterfactuals, and if you want counterfactuals, you're going to like break your trajectories like that. And I think there's kind of, my guess is there's no way around that.
Just aside, now that you've done, use something in your target that you wouldn't otherwise have done, to just go ahead and execute it and get the data. And,
Well, yeah, exactly. And in the online setting, that's probably the explanation for why this problem is not nearly as bad.